Hi, this is a presentation on the activities conducted by the U.S. Geological Survey, the U.S. Army Corps of Engineers, and the University of Wisconsin-Platteville to limit the spread of aquatic invasive species, in particular certain species of fish that have been proliferating through U.S. waterways after they had been introduced at various locations due in part to international shipping. So I'll begin with kind of a background and overview of why it was this project has been undertaken, what species of fish are being addressed, and then some of the financial impacts on both sides of the issue. Then we'll proceed to laboratory studies, how it is that we actually formulated this activity, and then the results of some field scale studies that gives rise to some conclusions and recommendations for further development. So many invasive species have gradually intruded in American waterways and international waterways for that matter. Sea lampreys are one example of a problematic species, a fish parasite that attaches onto native species. Formerly, they were limited to Lake Ontario and blocked from other Great Lakes by the Niagara Falls, but they have since been able to move past that border and establish themselves in the other Great Lakes. Another invasive species is the round goby, which is native to the Black and Caspian Seas, and this was brought to U.S. waterways through the ballast tanks of ocean-going shipping vessels. They eat native fish, their eggs, and take over habitats as well. So these two figures kind of illustrate how it is that the sea lamprey moved past its original limitations, and likewise the round goby has proliferated through the Great Lakes and is gradually intruding into the Mississippi River basin. So the Mississippi River Basin, as you can see, covers a good portion of the Midwest and is connected not only to the Mississippi River, but the Missouri, Arkansas, Red, Illinois, and Ohio rivers. And the establishment of invasive species within a waterway generally indicates that it can move throughout that waterway and affect other native species that would be living in those areas. In this case, the research is focused on a boundary between the Mississippi River Basin and the Great Lakes Basin, an area that actually has a shipping lock that presently serves as the main barrier between movement across those two waterways or Great Basins. So in the 1970s, some invasive carp were imported to fish farms in the US to control algae growth, but flooding in the 1970s and 90s allowed them to escape their original enclosures. Two problematic species have begun to establish themselves in the Mississippi River Basin. Those are the silver carp and the bighead carp, which can reach upwards of 100 pounds and consume 2 to 3 times their body weight daily. They eat a variety of different native plant life and outcompete native fish, mollusks, and other invertebrates, thereby throwing off the native ecosystem. Now, Asian carp have been moving through U.S. waterways, devastating local ecological areas and having significant impacts to fisheries and native fish. They've established themselves in the Mississippi River tributaries, but we hope to prevent them from establishing themselves in the Great Lakes, because if that were the case, all of these areas around this region would actually be red. So two major objectives have been used to try to deter the spread of these invasive species. One is to reduce the population in affected areas, and then other to prevent the spread to unaffected areas. So this is kind of a depiction of how it is that they've proliferated through the Mississippi River Basin since the 1970s when they originally escaped their enclosure. And you can see that the proliferation of dots more or less ends at the junction of the Great Lakes. That is the subject of this particular research. So if we zoom in on the Great Lakes area, this is really Chicagoland here and some of the surrounding suburbs. You can see the connection between the Illinois River on the lower left and the Chicago Area Sanitation and Shipping Canal with the Brandon Road Lock and Dam situated right between them. Here we see establishment of some moving species, but not necessarily those that are able to populate further into the Great Lakes. So the Brandon Road Lock and Dam is a pinch point between the Mississippi River Basin and the Great Lakes Basin, and it serves as a natural barrier with some human modification to prevent movement of species from one side to the other. So as you would imagine, there are many people concerned with the situation as it stands. There had been a proposal of a full lock closure that would have prevented shipments, that is to say, shipping by barge from the Mississippi River Basin to the Great Lakes Basin. And as you would imagine, given the tonnage through these areas over the course of a given year, roughly 12 million tons per year, the shipping industry certainly has some opposition to the proposal of a full blockage of the waterway. On the other hand, the fishing industry stands to lose profits of upwards of $8 billion in fishing tourism and associated retail. And so they've been pushing for the full closure of the Brandon Road Lock and Dam because the introduction of invasive carp could cause unknown effects, perhaps a full collapse of the sports fishing industry that is so lucrative for the Great Lakes states. So upwards of $7.2 billion would be exchanged or be at risk on an annual basis. And so many of these states have actually filed suit against the Army Corps of Engineers and the city of Chicago, asking for full closure of the locks and dams. Here we see the states of Michigan, Wisconsin, Minnesota, Ohio, Pennsylvania, and several Native American tribes have all filed suit for closure of that lock and dam because they don't want it to impact either their social or economic well-being. So the particular lock and dam in focus is at Brandon Road, situated in Joliet, Illinois, a little southwest of Chicago. And this, as I said, is the human-made pinch point between two basins. And the Army Corps of Engineers has proposed several methods to prevent migration, at least from downstream of the Illinois River, upstream to the Great Lakes Basin. Here we see a combination of air bubble curtain, kind of at the entry region of the approach channel. Some electric barriers have been included as well. There's a proposed acoustic fish deterrent, making use of various underwater sounds to prevent their further upstream migration. There's an engineered channel underway, and this is in particular related to what's referred to as the flushing lock. That is to say, the lock itself and efforts to introduce benign chemicals into the lock during times of lock rising and lowering to prevent the upstream migration of aquatic invasive species. So in general, they've used chemicals, bubbles, bubble curtains, acoustic, electric, and carbon dioxide barriers. This in particular pertains to the use of carbon dioxide barriers. So the way the study research began is my colleague Aaron Cupp had done some laboratory studies of the impact of various gases on the equilibrium of a variety of fish, and he had found that many fish exhibit avoidance behavior at carbon dioxide concentrations of around 100 milligrams per liter. Um, and so the figures on the right show actually three states of CO2 injection into a walled enclosure, basically a very large concrete aquarium, where the fish were in the originally just kind of general distribution shown there. Carbon dioxide was injected in this region, and all the fish moved, that is to say, avoided the carbon dioxide to the other region. And then after a few hours of gaseous dissipation, the fish returned to their normal equilibrium position. So he had brought the project to the University of Wisconsin-Platteville, and we have some civil engineering facilities that allow us to do tests that would be related to the development of a carbon dioxide infusion device. So we had used the open channel flume in the civil engineering laboratory, and we had set up a system whereby we could assess the carbon dioxide proliferation through the enclosure as a function of time. And we didn't know the most efficient method to inject at that time, so we tried 5 different configurations: a so-called space cone, contact barrel, porous stainless steel rods, a direct air hose, and then a Venturi nozzle. all with an effort to maximize the efficiency of carbon dioxide injection and to do so in a timely basis. In the illustration or the figure we have right here, you can see 5 pH sensors situated along the length of this open channel flume used to detect carbon dioxide concentrations from the injection region, shown right here, where we actually have the contact barrel kind of situated on top. So this is an example of the species cone. You can see carbon dioxide injection from above and simultaneous, actually water injection from above and simultaneous carbon dioxide injection from below, sending out a carbon dioxide infused water mix to be measured for its impact on the acidity, that is to say the pH measurement of the equipment. Another device is this venturi right here. It's difficult to see, but there's a converging diverging section right here, like an hourglass, and the upper hose there is injecting carbon dioxide into water that is being passed directly through the venturi nozzle shown there. So we had tested several different carbon dioxide injection systems, in this case, literally injecting gas into a liquid, and we wanted to assess the efficiency of each different configuration. So we bought a calibrated mass flow meter from Alicat, shown here, and that allowed us to measure the total mass injected with the superscript I of carbon dioxide over the course of the experiments. And we also were able to measure the dissolved carbon dioxide, superscript D, shown right there, as a function of the volume of the reservoir, shown to the right, and then the carbon dioxide concentration, shown in the middle there, which can be deduced from a calibration measurement that relates carbon dioxide concentration to the acidity of the water being infused with carbon dioxide. And the infusion efficiency was then calculated as the quotient of the dissolved carbon dioxide to the injected carbon dioxide, as shown in that figure. So the results of our preliminary studies showed that the species cone worked best, the venturi second best, then porous stainless steel metal, followed by the contact barrel, shown in order from left to right. And it was sensible to suggest why not combine all of these features into, or at least many of these features, into a single device that can perform them even more efficiently. So this leads into our field studies. I'll give a brief overview of the experimental setups, floor and wall manifold configurations, injection efficiency, and then what was important in terms of economics, what is the operating power of these systems. So we began our field studies at U.S. Geological Survey's Upper Midwest Environmental Sciences Center in La Crosse, Wisconsin. We had worked on one of these test ponds, shown in this area here, and basically equipped it with a range of different fluid machinery to efficiently inject carbon dioxide into the enclosure. So the enclosure dimensions were approximately 100 feet by about 44 feet. And the figure on the left shows what's referred to as the floor manifold. Then the figure on the right is what referred to as the wall manifold. Essentially, the difference between the two is the floor manifold had very big networks of PVC piping laid on the floor of the pond. Meanwhile, the wall manifold used an assembly of PVC pipe and steel pipe fitted to the wall of the enclosure itself and used to inject carbon dioxide over the length of the enclosure. So these actually use very high velocity nozzles. Meanwhile, these actually use very small holes drilled into the surface, and they've essentially injected the CO2 infused water in an upward direction. So a composite CO2 injection module was designed based on the prior research undertaken in the laboratories at UW-Platteville. We used porous stainless steel rods, as shown in the profile view right here, put inside a contact barrel, shown in the middle right there, which used a combination of turbulence and a general restriction, you could say, in cross-sectional area from entrance to exit. There, you could say by the presence of this area, there's an effective restriction that makes it behave like a venturi. So we combined several different operating principles, and then we used 4 carbon dioxide tanks with flow meters on them attached to each of the inlets of the contact barrel, and use that as part of a system to inject CO2 into water. So in total, actually, we used 8 tanks because they only had limited mass flow rates. So we were able to attain a mass flow rate of 16 pounds per minute with the use of a manifold connecting all of those tanks. And to give kind of a schematic of how the system was set up, it was a closed loop system. The water was taken in from the enclosure itself, pressurized through a pump, passed through a carbon dioxide injector, and then passed through the manifold, we'll say either wall or floor manifold, whichever was selected for the purposes at that time. The pump was able to provide a volume flow rate of water around 2,500 gallons per minute, and the CO2 flow meters were able to take totals of 125 cubic feet per hour, giving us the maximum volume flow rate of carbon dioxide. It's 1,000 cubic feet per hour. So this is kind of an actual photograph of the equipment setup. Here we have the test pond over to the right, that big concrete enclosure. The intake pipe isn't shown there, but it essentially goes into the diesel pump shown there, passes through the contact barrel, shown actually to the right there, with the CO2 hoses dangling down. So a water CO2 infused mixture then passes through this large hose right here and goes to the drop down either for the wall manifold shown here or the floor manifold shown here. So 2 different sets of tests were undertaken, both of which were used to assess the overall efficiency of injection. For the wall manifold, which will be seen in a moment, we use 2 different designs to maximize the momentum flux of the CO2 infused water such that it would maximize the mixing that occurs within the tank itself. The figure on the left was referred to as a converging nozzle, which is based on an actual fire hose design. And then the figure on the right is a converging diverging nozzle, which was intended to maximize momentum flux through the minimal cross-sectional area, but also induce some lateral motion to the fluid itself to see if it would improve mixing in the near range. This then is a depiction of our manifold showing 10 injection nozzles, 5 on each side of the enclosure. This is hanging on the wall, hence the name wall enclosure, and it's being faced into the pond that has yet to fill to a height of approximately 4 feet, as you can see from the water layer there. So this was submerged about 3 feet underwater and used to inject high velocity water into the enclosure and measure the time it takes to attain a certain concentration of carbon dioxide. So in addition to this, we needed to know the carbon dioxide concentrations within the enclosure. So we placed so-called SONS, or pH sensors, at several stagnation regions within the enclosure, and then various other important points that would allow us to get field plots of the actual CO2 levels. And we were interested in the mixing time that it takes for 95% of the mixing to have occurred in the slowest region. This, as you would imagine, is intended to resemble the Brandon Road Lock and Dam or various other locks and dams that are situated at pinch points for invasive species. And this is intended to model how well it would mix under high velocity flow conditions. These are a depiction of the SONS. They were weighted with steel plates to hold them at the base of the enclosure in the regions where the least mixing was likely to occur. So this is also a calibration curve, again, for carbon dioxide of concentration as a function of pH, or essentially using pH as a proxy for measuring the CO2 concentration, where in this case it would suggest that a pH of around 6.8 would mean a CO2 concentration of around 50 milligrams per liter. This was set to the fluid that was the water that was being used at that time. And this then allowed us to take measurements of pH, as shown in the figure on the left, and convert them to CO2 concentration, where decreasing pH, that is to say increasing acidity, correlates to increasing carbon dioxide concentration, as shown there. So the floor manifold exists mainly was shown on the east side of the branch, and injection holes were not on the west side of the branch. Here we see various carbon dioxide measurements from the base level of the water in the enclosure before it's treated to the high concentrations. You can see a range from about 5 milligrams per liter to around 70 milligrams per liter at multiple pH or acidity sensors located within the enclosure. Elsewhere, the wall manifold, shown in the figure on the right, exhibited more uniform mixing. We still see the increase of from around 5 milligrams per liter to around 60, 70 milligrams per liter, but a greater density, you could say, clustering, you could say, of the concentration curves for several different positions within the enclosure. I should point out the wall manifolds were actually down at this location, and these clusters of sonde measurements, a total of 12 sets of measurements for each test, are shown in the locations A, B, and C right here, which correspond to the far wall, the mid wall, and the close wall mixing locations. So the greater the concentration of these lines of carbon dioxide concentration themselves, the better the mixing occurs within the enclosure. So we've got mixing homogeneity is an important factor. It's important to make sure the mixing is uniform throughout the enclosure or on an advantageous gradient if necessary. Meanwhile, the converging diverging nozzle showed greater irregularities than the converging nozzle. Here we see less mixing homogeneity within the enclosure, both at the far wall as well as the close wall, and so this didn't prove to be as desirable for long-term mixing. Now, for efficiency measurements, we had taken a similar approach as for the laboratory, but in this case, the field studies required a slightly different tactic. Initially, we had intended to use volume flow meters, and use those to calculate the mass flow rate, but we found that we could get more reliable results with a physical scale, which measured the change in mass of the 8 tanks that were being used for the carbon dioxide injection. So again, we've got mass injected on the equation on the left, and then the similar approach to the laboratory studies, we use the carbon dioxide concentration, in this case, the mean of the 12 measurements, times the volume of water contained within the enclosure to get the dissolved mass of carbon dioxide within the enclosure. And the efficiency was used the same quotient of dissolved to injected carbon dioxide. So the tests had been broken out by design of experiments into 4 experiments for each configuration of floor versus wall manifold, and then each configure or each type of nozzle within the wall manifold, both converging and then converging diverging nozzles. And we had taken the measured injected masses, measured more or less from the change in mass of the tank itself, and then the calculated dissolved mass with the uncertainty in the calculation shown right there to determine the overall injection efficiency, which is very much a function of water flow rate and carbon dioxide flow rate in addition to the configuration of the enclosure itself. So for the most part, the wall manifolds using high velocity flows and nozzles had better mixing efficiency than the low velocity flow of the floor manifold itself. So those seem to be the better prospects for installations for a full scale installation. So a lot of valuable information was taken from these experiments, one of which is if operating costs are the highest priority of the system, then it's better to go with floor manifolds, which operate at low pressures and can make continuous operation at relatively low costs. They, on the one hand, have lower efficiency, but they also have lower operating costs and they result in lower turbulence, which means minimum disruption to maritime traffic. In contrast, if operating costs aren't a concern, or if you can go with intermittent operation, such as the Brandon Road Lock and Dam or various similar locks and dams, then it would be best to use wall manifolds in a closed system configuration where the treatments are essentially transient flow instead of steady state flow. They, on the one hand, have higher efficiency, which is desirable, but higher operating costs, which isn't so desirable, and they result in higher turbulence, which is dangerous to small boats or people who may be in the immediate vicinity. And it also presents a greater obstruction to maritime traffic. So the results of this research were published in the ASME Journal of Fluids Engineering under the name Thomas Salper, Aaron Cupp, and David Smith of U.S. Geological Survey and U.S. Army Corps of Engineers. Find that online for free if you'd like to read more. Currently, the project is being scaled up to a larger field scale installation to be conducted at Kakana Lot number 2 on the Fox River in summer of 2019. The blueprints have already been set up. Some arrangements are being made for the installations, and we expect to have the lock in place and full scale field trials underway in summer of 2020.